start recording and it'll work. Boom, we're recording. Okay, coming to you live from my office in my house. It's me teaching you about science. What else is new? Am I right? Okay, so y'all want to see what's going to be on the quiz? You can have this study guide. I made it for you. You saw this on Friday. We have a quiz tomorrow. It's over the topics of the inside of the Earth and earthquake waves. Big stuff. You're going to be able to answer these 8 questions. If you can do that, you're looking at a 20 out of 20 on the Quizzy Boy, okay? So I really want to kind of point you in the right direction for where to get access to some of the stuff for reviewing. I also want to make sure that you have answers if you, things that you don't really know about. So if you've got questions, throw them in the chat. If you're like, I don't really know what to do about this one, put it in there. Where do I look to find information? You throw it in there and I can see it and I'll get right to it. I'm going to respond directly to your questions in the chat. Also, you can give me feedback like, wow, it's really loud, or no, I can't hear you, or like, there's some other weird sounds happening in the background, and I'll probably tell you that it's my dog licking his toes, but it's the way that is. Okay, cool. No questions? I'm confused on question 8. That's a great place to start. Okay, so let's take a look-see at that one, huh? So what I wanted to focus on the most, actually, so the inside of the Earth is very hot. Inner core is hotter than the surface of the sun. How did it get that way? How does it stay that way? And why is the crust cool? Okay, let's dig in. So, as you probably saw, and the reason that I have all this stuff pulled up is so we can look at it together. Okay, we've got the greatest discoveries here with Bill Nye the Science Guy. Okay, we can watch this video together, but we're not going to do that. So Bill in here, he's chatting with our friend Dr. Katherine Johnson. Sorry for the potato quality. My monitor's relatively large and this video is optimized for like 480p. But during this video, right about at this time actually, you see this image is the early molten Earth. Okay, so as Earth is forming, all these things are crashing into each other. Okay, and by things I mean planetary bodies, stuff out in space. Okay, I'm gonna get out of this. So there's stuff out in space all crashed into each other, and you can see me. I'm gonna show you. Ready? So we've got some things, some other things, and they're going to collide together. This is the way that planets and stars and things form. Objects in space produce a gravitational attractive force, which pulls in other objects in space. The closer they get, the more attracted they are to each other. We're going to learn more about that actually in the next couple of weeks in my class. We're going to do some gravity simulations. So objects are going to collide. They're going to come together. Those colliding objects are going to produce heat. Right, because when things collide, there's a lot of energy. So the potential and kinetic energy that these things have when they come together is usually transferred mostly to heat because there's not much else it can be transferred to. It's kind of like how on Earth, every time we touch a surface, there's friction, and that's kind of how some of our energy gets dissipated. It doesn't go away, it just changes form. So anyway, that heat is what caused things to get very hot. The rock, the metal that make up the Earth now, those things all got molten like they did in the video. Here, okay, so right around this point in time in the video, she's showing us this molten Earth. There we go. So you can see, we can watch Minecraft videos if you want. So we got this molten Earth, right? And that is the heat that got there in the first place. How does it stay that way? Well, it stays that way because the outside of the Earth is actually a solid layer of rock, and it holds some of that heat in. It's hard for all of the heat to escape. It escapes through like volcanic vents and things like that, but it's not going to get out very quickly. And our Earth has been around for 4.6 billion years, and it's only maybe like halfway there in terms of cooling off. We just have that very thin layer at the top, the crust, that's cool and hard and rock that we can live on. What's next on that? How does it stay that way? We did a little bit of that. There's one other heat source inside the Earth, and it's nuclear decay. So there's radioactive particles inside the Earth, just like there is everywhere, but those particles are decaying, and as those particles break down, it's kind of going to give off some energy. That energy is going to produce some heat. That heat allows the Earth to be heated from the inside. Okay, so that's part of what keeps it hot. So why is the crust cool and made of rock if everything else is molten and the Earth was once molten? Well, the outside of the Earth is the farthest away from the heat area, which the major heat sources are in the center, in the core, and in the outer core. The major areas of heat are not on the outside where the crust is, so the crust is cooling off. It is getting very rocky. So it was the first thing to cool off. It cooled off like 4.3 billion years ago, somewhere like 4 billion years ago. I don't know, I can't remember. Could have been later than that, actually. Could have been 3.5 billion. My late time memory is not very good. Okay, so that takes care of that one. How are questions 7 and 8 different? Well, question 8 is asking about how the Earth got hot, and question 7 is asking about the density. So let's look at this density thing, right? So y'all know, I'm going to have to type this probably. Let's come down here. Density equals mass divided by volume, right? That is literally behind my head. Here, let's move it out. There you go. So density is mass divided by volume. We're going to be looking at this, so I'll keep it highlighted for you. We're answering number 7. Why don't we move it up here to where question number 7 actually is, huh? That would make more sense, wouldn't it? Okay, so this is the major thing. So what's the most dense layer inside the Earth? Hopefully you all know that the center of the Earth, the core, is the most dense. It's solid iron, and on the outside of that is a liquid iron and nickel outer core. The inner core has to be a solid despite being really, really hot, hotter than the surface of the sun, because it's under so much pressure from the outside, whereas the outer core is under slightly less pressure, so it can be molten into a liquid, okay? The least dense layer is going to be the crust. You get more dense in the center, and you get less dense as you go out. So we live on the softest, fluffiest, lightest, least dense layer, but really, like, obviously it's rock, so rocks are hard. Okay, how did it get that way? This is the big difference. The big difference between 7 and 8 is that they're actually related. So when the rocks, there goes Chauncey, when the rocks are crashing into each other, okay, and the Earth is very molten and hot, it's kind of like you have a jar or a tube full of all these liquids, right? The most dense stuff is going to drop to the bottom. The least dense stuff is going to rise to the top. So you've got your materials, your minerals, your rocks, okay, your different types of metals that make up your crust floating up to the top because they're not as dense as the other metals. So like molten iron, for example, is very dense, so it's going to drop its way to the bottom. And the bottom of a spherical planet is in the middle, right? So from all sides, iron is dropping to the bottom, and the lighter minerals like your calciums and your magnesiums and your potassiums and your sodiums are going to be floating out. They're rising to the top, aka the surface. Okay, so 7 and 8 are actually closely related. In fact, they're mostly the same thing. Does that help? Are you hearing me okay? Cool. No response. That's how you know we're doing something good. Okay, good. Man, first poggers. It's good. We're going to celebrate that, you guys. Matthew, are you confused? Would you like some clarification? By the way, the answers to 7 and 8 are all found in the Bill Nye the Science Guy video featuring Dr. Katherine Johnson. You can dig that up if you start right around, where is the interview starting? Like 5.5 minutes in. Cool. Hearing me just fine. Cool. Good. So we're in there. Greatest discoveries with Bill Nye. I know that's really small. I'm sorry. But like, yeah, you know, about 5.5 minutes in, he's going to talk to you.
The core that Lehman had found was the Earth's inner core. Today, through precise seismic measurements, we know that it's made of solid iron.
Sure do.
Solid because gravity at the center of the Earth creates a pressure 3 million times the pressure it exerts on the surface. The core that Richard Oldham had discovered turned out to be the Earth's outer core. It's made of liquid iron.
So maybe this is a little early.
A hot churning mass.
So you probably could have gone to like 6 minutes before you started if you really wanted to know.
Create the magnetic field that protects the Earth from dangerous cosmic radiation. Together, the two cores that Oldham and Lehman discovered form a massive structure over 4,000 miles in diameter.
Okay, you guys got the picture. I'm going to go back and answer number 6 because that's what you asked about. Okay, so number 6. Explain why some places on Earth won't be able to detect P waves. Sure. I actually want to do 5 first, if that's all right. So let's take a gander at number 5. Oh, by the way, did you guys see that if you go to your Google Classroom, there's a thing, here's something that will help you prepare for the quiz. And there's like a clicky thing. When you click on it, it takes you here to the science tech book on Discover Education. It explains about how we see the inside of the Earth. There's all kinds of goodies in here. We've got an explore section, an explain section, Here we go, seismology. That's like the study of earthquake waves, right? So there's some good images that apparently aren't loading for me right now, which is good. There they go. Okay. Oh, I'm supposed to put things there? No, those images didn't load. This one might have. Yeah. Okay. So anyway, you can use that to help you. There's some good things in here. This is the teacher side of it, so it's going to look a little bit less put together than the student side of it, but it'll be good. All right, number 6. That's what you asked about. So for number 6, we're going to need a map so we can show you about P waves and about S waves. So I'm going to pull that up real quick. Let's see what I want to use. Probably this. Okay. Hopefully this is familiar. Wow, this is not optimized for my screen at all. Okay, so an earthquake is going to start on the white dot here. Okay, now I need to move the earth a little bit. Can I move it over here? Hex to the yes, I can. Check it out. We're remixing Earth remix. Okay, you too can be an Earth DJ. All right, let's take a look-see. So this is to show you like on the surface how the waves travel, but we're going to look inside the Earth, right? So we're taking the Earth as a globe. We're going to slice it in half, and we're going to look inside. So this is the wave moving through the layers of the Earth, okay? So when we play the earthquake, I'm going to turn the audio off because it's obnoxious. Okay, when we play the earthquake, the waves are going to start generating, and they're going to move out in all directions. So P waves and S waves leave at the same time, okay? And you can see that the P waves are much faster. That's one of the questions that you're going to have to answer. I think y'all can figure that one out on your own. Now, in this simulation that you're about to see, there's going to be lots of reflection. There's going to be lots of refraction, okay? So it's important that you pay attention to what's going on. We got a follower. That's what's up. Okay, so when the waves start to move through these different layers, you're going to notice that the speed changes, and you can actually look at the time up here in the left of the different waves to kind of see how they're going. I would say that you can ignore that because it is actually how these waves are hitting these seismic stations. That's why they have these weird acronyms in front of them. So like this is Christmas Island. Isn't that fun and exciting? Okay, so we can watch the waves move through. Now, reflection or refraction is gonna happen, but you don't need to have a very good understanding of that to answer the question. But refraction is more important than reflection. So any waves that bounce back, so if they go to you, boing, and they bounce back, we don't need that. It's reflection. Let's focus on the refraction where they change as they go through a different medium. So if they're crossing through a different medium, they're gonna go in a different direction, change speeds. Okay, so let's have a look-see here. Our P wave is just hitting the outer core here. There's going to be some reflection. You can ignore that. More importantly, there's going to be refraction. It's going to bend it a little bit. Oh, it played the sounds. It hates me. Okay, so do you see how this is no longer a rounded off wave? It's slowed down a little bit, actually. It's supposed to speed up, but that's okay. Maybe I don't actually know that much about what I'm talking about. Okay, so here we've got our refracted P waves, and do you see how it's separated up here in the corner and down here in the corner from the actual major P wave? So watch what happens as we finish this out. Only look at the red line in the front. Don't look at anything else. We'll look at that second. Okay, so do you see the separation between these waves? That means there's no P wave in that space. There's no P wave in this space either. So this is actually going to be number 6 before I do number 5. My apologies to everyone who was listening to me earlier. Okay, so these places from all through here are going to feel the P waves because the P wave front was actually able to reach them, okay? But you'll see there's a separation between here and here where they aren't feeling these P waves. You ignore the smaller, thinner line. It's not a major P wave. It's like a secondary wave. So, oh, that got really confusing. All right, I'm going to pause it so we can look. Your front of your P wave is here. There's a second line that's like filling in the gaps, but if you look at the more thick one, the one that's labeled PKIP, that's the one we want to follow, okay? That wave isn't going to hit every single place, okay? So what that's going to look like is, I'm going to Google it, and apparently you're going to be able to see anything that I previously purchased on Amazon. That's fun. Good, okay. I know this is from Quora. It doesn't really matter what it's from. It does matter that it's not loading, though. Fine, we'll use the National Geographic one. Open you up. Classic. I'm not going to sign in. Just use this guy. That'll work great. It's going to work great. Okay. Look, it's the same demo that I used. All right, so looking at our map of our Earth here. Yeah, it's acceptable to call it the shadow realm. That's fine. So we've got these waves, okay? They're going to come in. Some of them are going to go through the outer core, which is going to cause refraction, and that's why we miss a spot with our P waves. So this is a spot where the P waves don't get at all, and they don't get here either. So this is our epicenter. Same exact thing as here. This is our epicenter, so I can just rotate it if you want vertically, so it looks the same. Okay, there we go. So, oh wow, it's not taking that control very. It's not very happy about what I've done. Well, hold on a second. There we go. All right, cool. We did it. Okay, so these places in the middle, only the middle section is going to get P waves. Okay, so the P waves are going to hit here. So they do hit bam, 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 bam. All the blue is P waves, but they miss these sections. Okay, and that's due to a thing called refraction. Refraction is the thing you want to remember about. Refraction is when waves change speeds going into different mediums. So like I'm talking to you, right? My particles are vibrating the air particles. If I was trying to talk to you underwater, it would sound a lot different, right? Because the waves would be traveling at different speed. Especially if you were underwater and I was outside the water, you'd still kind of hear me, but it wouldn't be very good because of refraction and some other muffling effects that liquids tend to have. Okay, so that's your P wave 1. The S wave shadow zone is even easier. This is question number 5. That's even easier. S waves, they travel like this, right? They're like slither boys, okay? S waves are going to take that transverse path, which is this, as opposed to the longitudinal, which is like a spring, okay? They're going to take that path. The problem is they're shearing. They're trying to like shear. They can't do that in a liquid, okay? So since they can't travel through liquids and the outer core is a liquid, you can see that your S waves are just straight up going to miss everything from 103 degrees to 103 degrees on the other side. They're going to miss all that. Nobody down here is going to get these S waves. So only this top section on the left and this top section on the right are going to feel S waves. It's because of the outer core being liquid. It's not because of refraction. It's straight up because the waves can't travel through liquid. And that's number 5, number 6, number 7, and number 8. Okay, that's been fun. I stumbled over my words a lot there. So if it wasn't, like if it didn't make sense, just let me know. Again, this is being recorded. I'm going to post it on the YouTube after. Any more questions? Things you want me to cover? Things I don't know about? I mean, these things should be pretty easy for you. Number 4, I just talked about refraction a second ago. We talked about density just before that. So hopefully you can tie those things together and explain it. We will have gaming streams in the future. We will? Okay. If you say so. I do occasionally use my stream, this one, for my friend to see me when he dies and I didn't die in a game. But that doesn't happen very often because I mostly die first. Okay, so that's everything that I wanted to show you. Do you have any questions? Or are we cool? Things you want to know? I said I would set aside a class period's worth of time, and we've only gone 26 minutes. So that's not super far. You're cool. I'm also pretty cool. I'm feeling pretty cool. Chauncey's pretty cool. He's having a snooze. He moved a little bit. Look, check him out. He's having a little nap. It's like, Dad, when are you going to stop talking to the children? All right, so I'm going to stop the stream. I'm going to post this on YouTube. If you've got questions, please let me know. Encourage your friends to, get on there and have a look at the video. And yeah, it's going to go on my teacher YouTube channel. So you have to find me, the teacher edition on YouTube. It's not on Mr. B Science. That's not me. If that's on YouTube, that's not me. Okay. Thanks for coming by, and I'll see you tomorrow.